you can see the picture here. These look like nice two-armed spiral galaxies. When we look at spectrograms, here is looking at a spectrogram between 6 and 7 gigayears. We see that there are more than one spiral at any particular type. In this particular case, we can easily pull out 3 spiral arms, 3 strong spirals, m equal 2 spirals, at quite different frequencies. There's one with a very low pattern speed of 20 kilometers per second. This is being plotted. This is the frequency on this axis. This is the radius on this axis. And this is the circular frequency in the solid black line over here. You can see that most of the power goes between the inner limb resonance. That's this dashed line over here, and extending beyond the outer limb resonance, outer dashed line over there. The contours show the power, how much intensity there is basically in each of these modes. So there is this one spiral with a low pattern speed that has a co-rotation radius at about 11.5 kiloparsecs, so in the very outskirts of the disk. And then there are ones with a co-rotation at about 6 kiloparsecs, another one around 4 kiloparsecs. The disk is threaded by multiple spirals. Nonetheless, during this time period, 6 to 7 gigayears, if you look at the galaxy, what you see by eye is what looks like a single m equal 2 spiral. This is part of the nature of these simulations, that they always seem to produce systems in which by eye you only obviously notice one, but if you do the more careful work of going in and digging out the power spectrum of m equal 2 perturbations, there are actually more than one. Now, these amplitudes that you're seeing an integrated interval over there between 6 and 7. If we look at more detail in time, what we see is that the amplitude of the spirals is varying significantly from everything. This is during the interval between 5 and 8 gigayears. There are times when the amplitudes are close to 0, and then there are times when they reach quite large amplitudes. This over here is reaching an amplitude of larger than 0.25. The red slow spiral has the amplitudes given on this axis. So this is what we mean by the spirals are transient. They are flickering a lot. Their amplitude changes all the time. And this is an important fact for later when I start talking about migration, and you'll see why. Right, so we carry on. That's sort of a little bit about the nature, a little bit about the nature of spirals. Right, so here is now showing for the full simulation as a function of time, the spiral pattern speeds that we're able to pull out. There is this one slow spiral that I was telling you about before, and then you can identify a number of different spirals at different. The point sizes here are proportional to the amplitude of the spiral, whereas, so you see there's a lot of quite weak fuzzy stuff out here, a lot of weak fuzzy spirals, but then there's also clearly distinct spirals that are persistent over some time and then disappear. And this very strong outer one, we believe is an edge mode, and it's very persistent throughout. But at any particular time, you see more than one spiral. Now, we've run the simulation with variations in numerical parameters and in some of the physics. That's shown over here. Fundamentally, these all evolve very similarly. Generically, there's always a spiral in the outer disk. There's always an edge mode like this. And then there's a number of additional spirals that propagate the disk. The only significant exception to that is this model S4. In this model S4, what we've done there is we've made the softening so large that what happened was a strong bar formed, and that's what this feature is here. And then the structure of the disk changed. Strong spirals threading through the intermediate disk, and you only have. You can see there is always this edge mode present in most of these simulations, and then 2 or 3 more spirals threading through the rest of it. So this seems to be a generic property of what is happening in these simulations. Does that work? Okay, so the story that I want to tell you about first is about migration. And migration starts off with a very interesting paper. And it was a paper that was in response to this one that I'm going to show you first. This was a paper by Vila et al. In 1996, where they looked at the solar metallicity, metallicity of zero by definition. And they asked if this is the metallicity of the gas now. 4.5 gigayears ago, we compute that it was something like this. And where is solar metallicity 4.5 gigayears ago? And what they found was that it would have been at around 6.6 parsecs in radius. So they argued that the sun didn't form where it is now, but it formed inside its current location by roughly 2 kiloparsecs. So the sun now had to go from here to here. So this paper provoked an interesting reaction. Jerry Selwood possibly spoke about this morning. What they showed was, this was Binney and Selwood in around 2000. What they argued was that a typical star is unlikely to migrate from its galactocentric radius of birth by more than about 5% over its lifetime. This is because this radial migration is caused either by stochastic scattering by either spiral arms or by dense gas complexes, molecular clouds. Now, that type of scattering can be constrained by the random motion in the disk. And we can observe that directly, the random motion in the disk. And we didn't need Gaia for that. That was already done for us. That was already done for us by Hipparchus. And this is what Damon and Binney did in 1998. These are the velocity dispersions. These are the different components of the velocity dispersions we observe in the solar neighborhood. This is Hipparchus, so very nearby. So this is the vertical direction, and I believe this is, roughly speaking, the radial direction. Not quite, because the tensor doesn't quite point to it. But the difference is not very large. But you see the velocity dispersion doesn't get very large over here. It only gets to about 40 kilometers per second. And then you can compute by how much the radius of a star changes over its lifetime due to this random motion. And the answer for values like this would be about 1.3 kiloparsec. I should point out that this is not the radius itself that's changing. This is the orbit becomes more eccentric. So it's not even that it remains on a certain orbit. So they argued, Binney and Selwood argue that, well, therefore, the sun could not have been born at 6.6 kiloparsecs. It had to have been born much closer to where it is now. And the reason why we see it discrepant from the gas metallicity is because the gas metallicity is not as uniform as we think it is. That was the initial paper. Then something very interesting happened. Shortly afterwards, these authors, to their credit, noted, great credit, noted that, in fact, their calculation wasn't quite right. That while they had treated the molecular clouds correctly, they realized that the spiral arm of influence was, in fact, much larger than they had thought. And the paper is withdrawn. Paper withdrawn because its principal conclusion is wrong. What they say is that the paper seriously underestimated the ability of spiral arms to shift the radii of stars that co-rotate with them. Co-rotate part, that's important here. Okay, so we carry on. What's their argument? So let's imagine that we are in a disk. The disk has a spiral arm. The spiral, or has a spiral, not a spiral arm. The spiral is, let's say it's rotating uniformly. We know that we can boost ourselves into a frame that is rotating with the spiral. In that frame, the spiral is stationary. So we have a time translation symmetry. Because we have a symmetry, Noether's theorem tells us that there's a conserved quantity. That conserved quantity is the Jacobi energy. EJ, which is the energy, the usual energy minus omega p times L. If that is a conserved quantity, any changes in angular momentum that a spiral cause have to be related with the change in energy through this little formula. This is just delta EJ equals 0, which leaves you with delta E is equal to omega p delta L. That's for a steadily rotating spiral. So we put ourselves in the phase space. This is angular momentum on this axis. This is energy on this axis. We have the locus of circular orbits by this black line over here. At fixed energy, stars cannot have more angular momentum than a circular orbit. So this is all in accessible space or on physical. And if the star has an energy here, an angular momentum that's lower than the circular, then it's an eccentric orbit. In disks, most stars will be along this locus. You get maybe to the to most bound. This is the hot region, and stars here will be on the circular orbits. Now, this simple formula tells us that the effect of a spiral is to move stars on lines parallel with slope omega p. So it will move stars on lines parallel to this. Then we can also ask, what is the change in the radial action as the spiral perturbation moves the stars around? And they computed that the change in the radial action, delta JR, is omega p minus omega times delta L over kappa, the epicyclic frequency. Now notice that when you are at co-rotation resonance, when the star omega is equal to the omega p of the spiral, delta JR is 0, and you can have a change in energy or angular momentum without changing the circularity of the orbit. And pictorially, what that means is you go from one circular orbit here to another circular orbit to first order along this tangent point over here. Rotation would be over. And this can happen while the spiral is changing the angular momentum of the star. Another way of thinking of that is if you plot the angular momentum and the change in angular momentum, these are simulations of the type that Jerry probably told you about this morning, where he seeds a spiral in the density by introducing a groove. It causes a strong spiral. And then what we see is that if this solid red line over here is the co-rotation resonance, stars inside the co-rotation gain angular momentum. Those that radii larger than the co-rotation lose angular momentum, and you have this exchange of angular momentum. Overall, there isn't a big change in the density, but there is a big exchange of stars. So you're shuffling stars around. This is for all the stars. This effect is even stronger if you have nearly circular orbits. You can see that there's even more distinct changes in angular momentum here compared to there. Now, all this is happening. While all this is happening, if you look at the radial velocity dispersion as a function of radius, the co-rotation resonance now is here, this solid red line. Light gray shows you what the velocity dispersion was before the spiral at the start of the experiment. Dark gray is at the end of the experiment, and you see that there's very little heating taking place over here. There is heating here. This is the inner Lindblad resonance of this particular spiral. Over here, the spiral will make stars move away from circular orbits, but at the location where there is the strong angular momentum exchange, very little of that is happening. And the way to think about this is the spiral is a wave, and you have a wave-particle interaction. The particles are the stars, and the stars are gaining energy and angular momentum, or losing energy and angular momentum. Wave. And that's exactly like the surfer. The surfer will gain the surfer will gain energy from kinetic energy from the wave if he puts himself at the same speed as the wave, and then he's constantly falling and gaining energy from the wave. And that's what's happening here. There's a wave-particle interaction and a form of Landau damping. Okay. So the place where we first got interested in this particular process was when we started thinking about the outskirts of galaxies, their density profiles had been noticed in early work by van der Cruyt in 79, that if you take images of galaxies, in particular edge-on galaxies, but also face-on ones, and as you push the contrast of the images, what you notice is that the galaxies start to look thicker and thicker. So this is the contrast that gets thicker, but it does not extend to larger and larger radii. It seems like there is a hard edge to this galaxy. This is contrary to sort of the usual picture we might have, that galaxies are pure exponential throughout. There is, in fact, an outer radius, van der Cruyt was arguing, at which the galaxy ends. Now, in modern CCD images, we have a slightly different picture, that the galaxy does extend some distance as an exponential, and then there's a break. There isn't quite this sharp end or truncation. There is a transition to a much steeper exponential. And here's another example of that. And in modern images, if you look at a galaxy, this NGC 5300, the location of this break, here, this red annulus, and you don't see anything special happening there. There isn't a big perturbation evident by eye that you can see. These types of profiles, these are known as type 2 profiles. Type 1 profiles would be pure exponential all the way to the last measured point. These types of profiles are extremely common. They're more than half of cases in star-forming galaxies. They're a little bit less common in early type galaxies, but they're quite common nonetheless. So it's important to understand why profiles behave like that. And that was what we set out to do initially. So one idea that was in the literature was that the reason why the profile breaks, this was from Yupshai in 2004, was because star formation ends at that point, and well, the galaxy also ends, the stellar light also ends. So that's what we were testing here. These are the types of simulations I was telling you about before. I remember I showed you that the galaxies are growing. This is the density profile at 1 gigayear, at 5 gigayears, and at 10 gigayears, you see you have a break at this location of about 4 kiloparsecs at 1 gigayear. That rises to about 7 kiloparsecs at 5 gigayears, and by 10 gigayears, it's pretty much slap on at 10 kiloparsecs. The break is growing. Why is the break growing? If we look at the gas, we see that there's a drop in the gas density at that point. And more importantly, there's a drop in the star formation rate density at that. So fundamentally, the galaxy has a break at this location because there isn't very much star formation happening beyond that point. And because this is growing to larger and larger radii, if you look at the mean age, there's a profile. So the oldest stars are at the very center and increasingly young as you move out. What we refer to as inside-out growth of galaxies. It's doing what we expect it to be doing. Now, however, you will notice that there is some star formation in the outer disk, but there is very little actually of it. There's a lot more stars out there than this integrated little bit of star formation would imply. So that's one puzzle. There's more stars out there than you expect. Moreover, there is this other funny thing that you will know, is that the mean age increases outwards. I'll tell you why that is in a bit. But what this tells you is out here, the stars over here, for instance, are quite old. And at early times, there is essentially no star formation at all happening over here. What you conclude is this is an isolated galaxy. The only place where these stars could have come from is from the inner disk. These stars have moved from here to the outer disk via some process. And I'll spend some time showing you what we think the process is. But here is that stated in a different way. This is showing the probability that a star ends up at a particular, the probability that a star forms at a particular location given its final location. That's what the colors indicate. So this is the final radius. This is the formation radius. The dashed lines over here, that's this break radius that I was showing you before, pictorially. The dashed yellow line here is that break radius. Basically, we're saying that very few stars out here form there. And the way you see that now is that if we look at stars that end beyond 10 kiloparsecs, beyond this break, and we look at the formation radius, very little formed over there. Vast majority of them formed interior to that. So the next thing we need to do is to show that there is migration taking place. Now, before we do that, let's give an example, a specific example of a galaxy. This paper, you will notice, is 2007. This is the point at which we got very excited about the mechanism that we were working on. NGC 4244 is an edge-on galaxy. Roloff de Jong with the Hubble Space Telescope in a survey known as GHOSTS is looking at resolved stellar populations of stars in this galaxy. And what he was interested in was to see where the break happens as a function of age. So up here, stars are old. These are young main sequence stars. You'll notice that there is a break here where this dotted vertical line is. And that break continues to be the same location for young main sequence stars. And for the older stars, these stars are, if I remember correctly, older than 3 gigayears. So it doesn't matter what the age of the stars is, it's always the same break. Moreover, he noticed that the break is the same at all heights. You get gold points here, the yellow points over here are as he moves upwards in height. And the gray is the same. There's always a fixed location for the break. And the point where the simulations really got very interesting and very exciting was when we looked at a similar sort of analysis in our simulations. We looked, first of all, at all stars. If we look at the galaxy edge-on, there's an there, and the break was deeper exponential. This is all stars. This is the oldest stars. This inner exponential, and then there's an outer exponential there. And the very youngest stars, there's one exponential there, and then a very steep exponential. And so what you're seeing is that the break is at the same location for all ages. It's also the same location independent of how high up you look from the midplane. So from this, we conclude that the location of the break is being forced by this radial migration. I showed you earlier that the location of the break is increasing as a function of time. So therefore, the break at earlier times, let's say 3 gigayears ago, would have been over here, but it's changed as a function of time. Now, this type of analysis has been repeated multiple times, showing that there is also, by the way, there is an age minimum over here, because as you reach this point, you have young stars over there, but then the number of young stars drops off dramatically over there, whereas you have the older stars. So this point represents a location where the age is a minimum. And that has been repeated multiple times with resolved stellar populations, some examples given there. With unresolved spectroscopic studies, you see again age upturns over there, and even color profiles. Shortly after we wrote our paper, people immediately started looking at color profiles of galaxies and finding that there are that the profiles are bluest at around the location of the break. Why is there, if I go back one slide, why is there this age upturn? The age upturn is simply because as you go further and further outwards, the process of radial migration is stochastic. Sometimes you move outwards, sometimes you move inwards. That depends upon the frequencies, the pattern speeds of the spirals, and what your phase is relative to the spiral. So the further out you have to get, the longer it takes you, because it's a random walk. And so purely these stars have to be older in order to reach these larger. Let's go there. So in the meantime, there's been several other processes proposed for populating these outer regions, including multiple spirals, multiple patterns, including interactions with bars. There's also type 3 profiles, which probably have to do with heating processes. I won't go into all of those in great detail. I'll just say that if you're interested in the subject, We wrote a review a couple of years ago. It's in this. It's by edited by Johann Knappen and okay, so let's look a little bit at the processes that are actually happening in these simulations. Here are 3 examples of stars that migrated by large amounts. These are stars that are migrating outwards because initially we're interested in these outskirts of the galaxies. What you can see is that the stars will form at some radius, they'll happily evolve in radius, then suddenly they can have these enormous boosts to different radii over very short time intervals, or under a gigayear time interval. Others evolve much more, slowly. They'll reach sometimes stationary points and then increase again. Remember, we are explicitly selecting for stars that are moving outwards here, so this is why they look like they're only increasing in radius. But we can ask about properties of these stars, of their orbits. For stars like this that change abruptly in radius, there are 2 possible interpretations. One is that something chaotic has happened to them. They've been heated in some way. It doesn't look like they're heated because their orbits don't have very large radial oscillations. It looks like they went from one nearly circular orbit to another nearly circular orbit. Let's try to verify that. So what these sorts of particles are doing is they're interacting with a spiral like this. This is showing you the amplitude of the spiral. Line color at any different point is showing you the amplitude. And then we look at the orbits themselves with the same coloring, now in the frame of the spiral. And what you'll see is that the star is going about its orbit. It's got some nearly circular orbit with perturbation, with looping. It's not a perfectly circular orbit. This is in the rest frame of the spiral. And then it gets trapped over here by the spiral. It oscillates around there a little bit, and then it moves off to a different orbit with smaller radius. Now, the importance of the fact that the spiral amplitude is not constant, that the spirals are transients, is that you're trapped for a little while, but then as the spiral weakens, you escape, and you escape at some different. And all of these stars are doing this type of thing. You start on one orbit, one radius, and then you escape. And so the transience of the spiral is important. The spiral has to do this, at least a flickering in amplitude. It cannot be constant. We can look at where the stars that are going to migrate inwards and outwards are. Those that are going to migrate inwards, the contours here show you the spiral density that's rising. These are stars that are in front of the spiral. They are going to lose angular momentum. Stars that are going to gain angular momentum are slightly behind the spiral, so they're going to be boosted forward by the spiral. And this green circle here shows you the co-rotation resonance. This is the change in angular momentum versus angular momentum. This is the co-rotation resonance, and you can see that there's a lot of angular momentum exchange. We look at the change in energy over the change in angular momentum. Remember, that's the change in Jacobi energy minus omega p. That's the change in Jacobi energy. This should be 0 if Jacobi energy is conserved, and you see these distributions are very closely centered on. To look at the change in the circularity of the orbit, that change in the circularity is very small. This is of order 2%, a little change in. So fundamentally, what this is arguing is that the migration is not being driven by a chaotic process. It's being driven by the simple co-rotation resonance migration. This is sometimes known as cold torquing, because you take a cold population, a nearly circular population, you torque it, but it remains a nearly circular. The colors over here are showing you the wavelet transform of the x component of these orbits. If this was a chaotic process, the power, this is what the colors are, the power would be broken up in lots of little segments. The fact that it's varying continuously tells you that, in fact, this is all a very gentle process that's happening. It's really surfing on that spiral. So I think this establishes quite nicely that what we're seeing here is the cold torquing that Selwood and Benoit talking about. Okay, so what are the effects of this kind of migration? Well, I've already told you that we think that's an important part of how you populate the outer disk. But there's other processes that this impacts. One of them is if we look in the solar neighborhood and we ask, where are the stars in the solar neighborhood coming from? If we define the solar neighborhood as between these two dashed lines, so that in the simulation, this is between 7 and 9 kiloparsecs, and then we plot the radius of formation of the stars that end up in there, what we see is that there's a large amount of stars that end up in the solar neighborhood but did not form there. And the fraction of those stars that formed elsewhere is larger for the metal-rich stars, the stars shown by this red history. Most of the metal-rich stars in the solar neighborhood formed outside the solar neighborhood. It's only a small percentage of them. Another important effect is in the age-metallicity relation. If stars remained on the circular orbits they were born on, you would expect to find a strong age-metallicity relation, so you would expect a gradient like this. Instead, what the simulations show is something that is quite a bit flatter with a lot of scatter around it. And that is basically the effect, again, of migration, mixing populations across the disk. So you flatten that relation quite a bit. Right. Now, observationally, this has now been measured multiple times. I'm showing you here 3 examples of where the age-metallicity relationship has been measured. One is using astroseismic ages for red giants from Kepler data set. You see that relationship is flat. Gaia ESO from spectroscopic data has measured ages of F, G, and K stars. Again, the relationship is quite flat. And this is an interesting study. This is a small sample, but it's white dwarf plus main sequence stars, which can be studied quite accurately. And again, you find a fairly flat relation. If you bin that data set, it looks like this. The relationship is quite. So the age-metallicity relation seems to have been affected by migration quite substantially. Another effect of migration is that it tends to weaken metallicity gradients in disks. This is from the Geneva Copenhagen survey. You et al. Looked at the slope of the metallicity profile. This is dFE/h dr. This is the effective temperature here. So these are younger stars than these stars over here. There's a gradient for the youngest stars, but increasingly as the stars age, as migration has time to shuffle them around, that gradient decreases. So we're seeing the effects of migration in the Milky Way. And one nice piece of evidence, I think, is when you look at originally in the Apogee survey, and you look at the metallicity distribution function for stars near the midplane, what you find is that for stars that are close into the center, you have this black histogram with a long tail towards low metallicity and negative skewness. But increasingly, as you move outwards, and here you're looking outside the solar cylinder, that skewness is positive. You have a long tail towards high metallicity, not low metallicity. Clearly see the shape of that skewness change. In the simulations, if we just look at where stars are born, we always find the metallicity distribution function with a tail towards low metallicities, so a negative skewness. But actually, when we look not at where stars form, but where they end up, the picture changes dramatically. We have at small radii a negative skewness, and that increasingly becomes positive skewness as we move. And what's happening is that the stars that migrate, shown here by the solid line, they're coming from smaller radii. The stars at smaller radii have a higher metallicity. There's a metallicity gradient. It's not completely erased. And so therefore, you're contributing to any location more and more stars that have migrated with high metallicity. And so what ends up happening is that the skewness changes in this way. If we take the metallicity skewness from here and we plot it as a function of radius, apogee are these triangles. If we overplot the skewness from simulations, those are the colored points. What you see is that the simulation, first of all, frighteningly matches the observations. We don't usually expect to match quite in that much detail. And what's happening is the reason why these points are colored is so that you can identify them on this separate panel. What we plot here is what the migrated population, what the migrated percentage is within each one of these data, between each one of these points. And you see that as the skewness becomes more and more positive, the migrated population becomes. So by the time you reach roughly the solar neighborhood, this red point, you have that roughly 50% stars in the solar neighborhood have migrated from somewhere. So pretty remarkable property. So that's, I think, one bit of evidence that really strongly makes the case for migration in the Milky Way. Right. Right. Now, this has been modeled quite extensively in recent years, especially with Gaia data. This is one example of that. And I'm showing you down here some more examples of people doing migration modeling. So on this particular example that I chose to highlight, what they're modeling is when the stars are forming. So the star formation time. Where did the stars form? So that's also typically an exponential, a radial exponential decline now. And with what metallicities were the stars born? So there's some model for the stars there. And then the last question is how far did stars migrate during their lifetime? And they characterize that as an exponential, as a Gaussian, basically as a function of radius, where sigma rm8 is the width of this distribution. And they measure that at 3.6 kiloparsecs plus or minus. Stars have migrated by quite a bit throughout the galaxy, throughout the evolution of the Milky Way. That's a quite remarkable effect. And people continue to study migration there. I'll show you a little bit more before I move on. Right. Here's simulations from the group of Rolf Schoenrich et al. What they show is that as a function of age, stars that end up in the solar neighborhood have had large radial changes in their angular momentum. This is roughly stars forming now. They will not have had much time to change their angular momentum, but for the rest of the stars, they have a lot of changes in their angular momentum. Stars are migrating. There have been variants of migration that are worth mentioning quickly. One of these is by Grant et al. What they find is that in their simulations, the disks are relatively low mass. Because the disks are relatively low mass, they support a large number of spirals. You can see all these spirals within the disk at any given radius. There's a high multiplicity of spiral arms, and there are spiral arms threading everywhere. These are some examples of stars. These are inward migrators. These are outward migrators. You see they're sitting on different sides of the spiral. They're there and there. Now, what they found was that if they looked at their pattern speeds, circular velocity is the solid black line. Because they had so many spirals across, they find that the pattern speeds of the spirals are always quite close to the circular frequency. There's always one more spiral. So what's happening in these simulations is that if a star is in co-rotation over here, it will move outwards, let's say, and then it remains in co-rotation with a different spiral, and they ended up with stars having really large radial migration beyond the 3.6 kilo. Huge amounts of migration. That was one thing that was different in that study. Game is frozen. There we go. Ivan Minchev has been arguing for a while that if there is a bar, and the Milky Way, of course, has a bar, the interaction of a bar and the spiral gives rise to even faster migration. These are examples of delta L versus L. If there is a resonance overlap, the exchanges in angular momentum basically explode very rapidly, and they predict that the entire migration should mix the entire disk in the space of about extremely fast. This would mean that there are no metallicity gradients in galaxies at all because of the mixing, especially if you look at stars that are older, there should not be any metallicity gradients. This can be tested, of course, observationally. This is this is now using simulation instead of before you were looking at let's call them toy models, tracer particle calculations. These are now simulations, and he argues here that the fact that there's a bar and the spiral, this gives rise to. But notice this is all happening fairly quickly on 3 gigahertz. This can be tested. Yes, that's the next slide.
Excuse me, Victor. You have just 5 minutes.
5 minutes.
Yeah.
Yes. Okay. Right. So I'm running a little bit slow. Basically, what you're seeing here is that if you look at the gradients of metallicity or of age, you don't find very strong differences between the barred and unbarred galaxies in terms of the metallicity gradients. What I think I'm going to do, because I only have 5 minutes, I'm going to skip through some of this, and I'll get to this. Apologies, I was going slower than I expected. Let me just show you a few more results quickly. There's been arguments about whether it's only the thin disk or also the thick disk that can migrate. This is an experiment from Jerry Selwood's group, former student of Jerry Selwood's, where they show that indeed there is migration in thick disks as well. And what they also showed in that study was that barred versus unbarred doesn't make a big difference. One of the surprising things that they found was that the vertical action is not a conserved quantity. It's conserved on average, but individually on a star-by-star basis, the vertical action is not conserved. And the most recent work on that is this, Mikola et al., where they show that as a function of angular momentum versus vertical action, the amount of migration, so sigma of the change in the angular momentum, is not a very strong function of the vertical. And we see something similar also. Topic from migration, otherwise I will only have spoken about migration. And I'm going to talk briefly about, apologies that I need to miss all this. I'm happy to answer questions. Right. The other thing I want to talk about is the vertical motions induced by spirals. Here is a simple toy model simulation with a strong spiral in it. You can see the strong spiral is given by this red line. If we ask as a function of height from the midplane, where does the density peak? It peaks, the midplane is the black, then you go to one scale height upwards, that's red, another scale height upwards is green, and then blue is the last scale height up. Black is always on the leading side here. Rotation is going towards smaller angle. So in the midplane, the spiral leads in some ways. And now we ask, what is the effect of that on the motions in this phi z plane? Phi z plane, so phi versus z. The sense of rotation here is towards smaller angle. So stars come in from the right and move towards the left. This is inside co-rotation. So stars are overtaking the spiral here. And what you see is that as stars enter the region of the highest density of the spiral, they are pulled towards the midplane by the overdensity, Gauss's law basically, of the spiral. So stars on both sides also appear. They move towards the midplane, and as they exit the spiral on the opposite side, they move away from the midplane. So there is a breathing motion going on here. They move inwards towards the spiral when they enter the spiral, and they move outwards away from the spiral. Now, if we had been looking outside co-rotation, the spiral would be going faster than the stars. Then you would expect these colors to be reversed. You would expect the red to be there, the blue. Go to the next slide. So we talk about breathing motions, where what we do is we take the difference between above the midplane and below the midplane. The motions are compressive when v breathe is less than 0, and they're expanding when v breathe is larger than 0. This is for the same simulation. You can see there's yellow values here. That means there's motions that are positive, so they're expanding motions there. They're moving away from the plane. This is the co-rotation resonance over here. What's happening, the stars are coming this way, they're entering the spiral, and as they exit the spiral, they're expanding quite abruptly. At larger radii, you see more of these bluer colors, and so basically at co-rotation, that you've had this inversion. Now here, stars are being overtaken by the spiral, and it is in those regions, therefore, that the motions are towards. This is if we include all the stars, everything from 0 to 3 scale heights. If we skip stars near the midplane, if we ignore the stars near the midplane, and the motivation for that, as I come back here again, is you'll see that there's very low motions over there. There isn't very much breathing motions there. And we go from 1 scale height to 3 scale heights, this becomes clearer. There's motions motions away from the midplane over there, and those motions away from the midplane happen on the different side after crossing course. This has now, we've now got Gaia that can measure velocities for us in some volume. These are the vertical motions for stars at different slices and heights. If this is looking in the XY plane, this is looking in the RZ plane, you see that there are motions that are different between one side of the disk and the other. And if you compute the breathing velocities, like I showed you before, a little bit to get through this. This is the breathing velocities as seen by Gaia data and Gaia data release 2. You see that there are motions away. Sorry, these would be negative is towards the midplane, and positive is away from the midplane. There are breathing motions that get larger as you move away from the midplane, basically. So these have been seen now by Gaia. We can see these quite clearly, and almost done. I think I have 1 or 2 more slides. Beside that, however, there is not just breathing velocity, there's also bending velocities, and that's where instead of having a minus sign in between here, now you have a plus sign. This means that everything is moving upwards or everything is moving downwards there. Spirals don't cause very strong examples of that. They do cause them, but not of sufficient amplitude to be comparable with the Milky Way. We have a paper in preparation on that. That should be out later. And I think I will stop here. I'll put up my conclusions. I think I've probably run out of time, so I'll just